So now we are coming on to the last portion of this lesson, theoretical aspects. Then we have to do a lot of problems. Okay, so with this video, this lesson of solutions is getting over, because the last two topics of this lesson, that is abnormal molecular mass and want of factor, that is deleted from the syllabus for this 2021 academic year. So with this video, we are coming on to the last part of this lesson. With that, all the theoretical aspects of this lesson is over, and now we have to do with lots and lots of problems, because in this lesson, whichever problem comes, we must be able to do all the problems and get very good marks or full marks perhaps. Okay, so now let us start. The last topic, that is colligative properties and determination of molecular mass. Okay, molecular mass of what? Molecular mass of solutes, okay, in the solution. Okay, so colligative properties and determination of molecular mass of solids. So this word colligative properties, I think that is new for you, and determination of molecular mass of solutes, how we can find out the molecular mass of the solutes via the colligative properties of solutions. Okay, so let us start. The properties of solutions, which depends upon the number of solute particles, all of you listen here, which depends on the number of solute particles and not on the nature of the solute particles, and not on the nature. Okay, so even if it is acetic acid or benzene or whatever it is, okay, we are not bothered about the nature, but we are bothered about the number of solute particles and not on the nature of the solute particles. Such properties of solutions are called colligative properties. Okay, now look at this point. If two solutions, not components, two solutions A and B have the same number of particles, the two solution will have the same colligative property. Okay, the colligative properties of both the solutions A as well as B would be the same, irrespective of the nature of the particles. Okay, whether these particles are glucose particles or sodium chloride particles or sugar particles or any other particles for that matter. Okay, if two solutions, I'm not talking about components, if two solutions A and B have the same number of particles, then the two solutions will have the same colligative properties irrespective of the nature of the particles. Is it clear? So now we are going to study the colligative properties. They are 4 in number that we have to study. Number 1 is relative lowering of vapor pressure. Number 2 is elevation in boiling point. Number 3 is depression in freezing point. And the number 4 is osmotic pressure. So I will be discussing in detail about all these colligative properties. So I hope this. So we can also say we can also call these colligative properties as democratic properties, because in democracy the number of persons count, isn't it? So now the first one, relative lowering of vapor pressure. Initially I'll give you some introduction. Suppose we are talking about glucose in water. Okay, for a solution of glucose in water. So initially we were having only water and we were finding out the vapor pressure, and then we are adding glucose to it, and now we are saying this is a solution of glucose in water. For a solution of glucose in water, see, glucose is non-volatile. Are you able to understand? So it is not adding anything to the vapor pressure. So the vapor pressure of that solution is due to water alone or the solvent alone. So in that case, Pa is equal to P0A into XA. That means the vapor pressure will be dependent on the mole fraction of water in that solution. Am I right? So Pa is equal to P0A into XA. Now Pa is equal to P0A into, for this XA I have written 1 minus XB. Is it okay? Because XA plus XB is equal to 1. Is it clear? So I am writing it as, see, I have put it as Pa is equal to P0A into 1 minus XB. Now this is the continuation. Okay, so Pa divided by P0A is equal to 1 minus XB. XB is equal to 1 minus Pa divided by P0A. Is it okay? Now XB is equal to P0A minus Pa divided by P0A. Very, very important equation we have to use for the problems. Okay, so XB is equal to P0A minus Pa divided by P0A. Is it clear? So now let us see what are these things. Okay, now P0A is the vapor pressure of water minus Pa is the vapor pressure of the glucose solution. So P0A minus Pa is called the lowering of vapor pressure, and this is always less, because the vapor pressure of a solution is less than the vapor pressure of the pure solvent that we have studied. Okay, so now XB is equal to P0A minus PA divided by P0A. If P0A minus PA is called lowering of vapor pressure, then in that case P0A minus PA divided by P0A is called the relative lowering of vapor pressure, because we are studying it with respect to P0A. So this is an alternative statement for Raoult's law. What is that? The relative lowering of vapor pressure for a solution containing a non-volatile solute is equal to the mole fraction of the solute in the solution. Is it very, very clear? XB is equal to P0A minus PA divided by P0A. So what is this whole thing? Relative lowering of vapor pressure. So relative lowering of vapor pressure for a solution containing a non-volatile solute is equal to the mole fraction of the solute in the solution. Is it clear? Now again I have written RLVP. Relative lowering of vapor pressure depends on the mole fraction of solute and does not depend on the nature of the solute. Therefore, it is a colligative property. Once again, relative lowering of vapor pressure depends upon the mole fraction of the solute and not on the nature of the solute. Therefore, relative lowering of vapor pressure is a colligative property. Now, I am substituting this XB, the value of XB. XB is equal to NB divided by NA plus NB. Okay, so NB divided by NA plus NB is equal to P0A minus PA divided by P0A. Now for NB, number of moles is equal to weight in grams divided by molecular mass. Okay, so I am putting it as WB divided by MB divided by WA by MA plus WB by MB. But you know that the amount of the number of moles of the solute in the solution is very, very less. So we can neglect it in the denominator. We can neglect it in the denominator. So what do we get the equation as? P0A minus PA divided by P0A is equal to, see here, WB into MA. See, this is in the denominator. So WB into MA divided by WA into MB. Is it clear? And what are we finding out? Why are we studying colligative properties? We are studying colligative properties of the solution in order to find out the molecular mass of the unknown solute dissolved in the solution, okay, indirectly. If you know it is glucose, I can easily find out that its molecular mass is 180 because glucose is C6H12O6. Suppose we are not being told that it is glucose. So how do we find the molecular mass of the solute? So MB is equal to P0A into WB into MA. You can remember in this way, WB is always in the numerator, MA is a greater degree, so MA is on the top, and then P0A minus PA. Okay, anything minus, that is less, so it comes down into WA. So MB is equal to P0A into WB into MA divided by P0A minus PA into W. All these equations you have to learn, or you have to recollect when we are doing the problems. Is it very, very clear? So that is relative lowering of vapor pressure. Is it clear? Now let us move on to the next one, elevation in boiling point. Have you ever observed, like we are taking water and it is coming to boil, okay, it's on the verge of boiling, but before it is on the verge of boiling, if we add a little bit of sodium chloride or sugar or whatever solute into it, it takes time to boil. That means the boiling point gets raised, okay, or elevated. So that is what we are going to study, elevation in boiling point of a solution on the addition of a solute. Okay, so the boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to atmospheric pressure. So you have to learn the definition of the boiling point, and probably I had taught this topic in chemical equilibrium part 1 last year. The boiling point of a liquid is the temperature at which the vapor pressure of the liquid becomes equal to the atmospheric pressure. Is it clear? So vapor pressure of a solution, we know that vapor pressure of a solution is lower than the vapor pressure of the pure solvent. Okay, so lower vapor pressure means boiling point is high. Can you understand? Lower vapor pressure, boiling point high. Higher vapor pressure, boiling point low. Therefore, boiling point of the solution is higher than the boiling point of the pure solvent. That is what I told. When we add salt to water, the boiling point gets elevated. Or we can conclude that boiling point of a pure solvent is raised by the addition of solute in it. Is it clear? Now, elevation, how much elevation is happening in the boiling point? So, elevation in boiling point is directly proportional to the number of moles of the solute in the given amount of solvent. Clear? Elevation in boiling point is directly proportional to the number of moles of the solute in a given amount of solvent, or delta Tb is directly proportional to small m, and small m is molality, or delta Tb is equal to Tb, small b only you can write, delta Tb is equal to Kb into m. Since m is equal to molality, not molarity, molality, Kb is also called molar boiling elevation constant. See, molar boiling elevation constant, which is defined as elevation in boiling point of a solution when 1 mole solute is added to 1 kg solvent. So this is a constant. So what is that? Kb. What is the definition of Kb? Elevation in boiling point of a solution when 1 mole of the solute is added to 1 kg solvent. Are you able to understand? Let us move ahead. Let me make it very clear. So once again, delta Tb is equal to Kb into m. Okay, and what is m equal to? M is equal to Wb by Mb divided by Wa by 1000. If I am not taking 1 kg, if it is in grams, we have to divide it by 1000, isn't it? So this is it. So I have written delta Tb is equal to Kb into Wb into 1000 divided by Mb into Wa. Is it very, very clear? Delta Tb is equal to Kb into Wb into 1000 divided by Mb into Wa. And what are we finding out from this elevation in boiling point? The molecular mass of the unknown solute. So what is Mb equal to? So from this we have to separate out Mb, and let us see what all things are on the right side. Mb is equal to Kb into Wb into 1000 divided by delta Tb into Wa. Is it clear? And there is also another name for this Kb. What is it called? Ebullioscopic constant. Ebullioscopic constant, and the unit is kg per mole. Okay, so we can conclude towards the end that boiling point of a solution, is equal to boiling point of the pure solvent plus elevation in boiling point. Boiling point of a solution is equal to boiling point of the pure solvent plus elevation in boiling point. Is it clear? Now, diagrammatically or graphically, we have to explain the elevation in boiling point. Okay, elevation in boiling point. So this is the graph. This is vapor pressure, this is temperature, and this is 1 atmospheric pressure. Is it clear? Now this is the graph for the vapor pressure of the solvent, and this is the graph for the vapor pressure of the solution. Always remember, the graph for the vapor pressure of the solution with increase in temperature is always below the graph for the vapor pressure of the solvent, pure solvent. Okay, now this is the point, it is reaching 1 atmosphere. So what is that? It is Tb. That means it is the boiling point of the solution. Okay, and this is the point. So what is this point? This is the boiling point of the solvent, T0b. Okay, so what is that? It is the boiling point of the solvent. Okay, and what is this difference equal to? Delta Tb, that is elevation in boiling point. Elevation in boiling point. Is it very, very clear to you? Okay, I hope this graph is also clear. Okay, vapor pressure, temperature, vapor pressure of the solvent with increase in temperature, vapor pressure of the solution with increase in temperature, and these 2 points, when we draw it down, this is Tb and this is T0b. Tb is the boiling point of the solution, T0b is the boiling point of the pure solvent, and this is how it goes. Is it clear? Okay. Now let us move on to the next 2 topics I'll be taking in the last video. Okay.